Good evening, ladies and gentlemen. Today our goal is to sketch polynomial functions using their roots and end behavior. As a reminder, roots are x-intercepts, and end behavior just talks about how a function behaves or what it's doing on the far left and far right ends of the function. Okay, let's get started with our first example. If we want to graph f of x equals the quantity x minus 3 times the quantity x minus 2 times the quantity x plus 7, this is easy. We see if we were to multiply this out, x times x times x would give us 1x cubed plus a bunch of other terms. The function has degree 3, the highest exponent on a variable is 3, and a leading coefficient of positive 1. Therefore, it's going to look like this cubic shape. We can see the roots are at 3, 2, and negative 7. Let's go ahead and plot these real quick. So all we need to do is fill in its end behavior and connect the dots. Nice. There's a nice sketch of the function. Okay. Let's try another one. F of x is negative 3x times the quantity x plus 2 times the quantity 3x minus 4 times the quantity x minus 7. Okay, again, if I'm multiplying out all the x's, I will get negative 3x times 1x times 3x times x. That would multiply to negative 9x to the 4th. Plus I'd have to distribute a whole bunch of other terms. But I can see it's degree 4, okay, so it's got to be parabolic, maybe facing up, maybe facing down, with a negative leading coefficient. Oh, that means the end behavior, or at the left and right ends, will look like this. Okay, let's find its roots. Oh, this one's easy. There will be a root at 0, because if x were 0, negative 3 times 0 is 0, times a bunch of other stuff, you're going to get 0. So the y value is 0, it's a root. There's a root at negative 2. Nice. Well, there's a root somewhere, wherever 3x minus 4 is equal to 0. Oh, so there's a root when 3x is 4 or when x is 4/3. And a root at positive 7. Okay, my end behavior looks like this. That means that the far left side and the far right side, the function is pointing down. Oh, again, we can just connect the dots. This is a rough sketch, so maybe in reality it looks like this, has this dramatic dip and a shallow max over here, or maybe it has a dramatic max over here and a dramatic, we don't know, right? But the point is, any of these would be fine. You're just showing it goes down on both ends, and we can connect the roots, which are clearly lit. Okay, example 3. What if f of x were negative 3x times x plus 2 squared? And here you get an x squared times negative 3x, that is negative 3x cubed, plus a bunch of other terms. Well, I know a cubic function could look like this or this. With a negative leading coefficient, it's got to look like this. I can see my roots are at 0 and negative 2. So to the left of negative 2, my function points up. To the right of 0, I've got to go down. Does it look like perhaps this? Or do we slice through the x-axis at negative 2 and then just bounce off the x-axis at 0? The key is looking here. It's called the multiplicity, or the exponent on a factor, x plus 2. Right? The degree is the highest exponent of the whole function. The degree is 3. But this factor, x plus 2, has multiplicity 2. Anytime the multiplicity is even, it creates a bounce off the x-axis. That is, at negative 2, instead of going through the x-axis, the function is going to bounce right off and then go through the x-axis or slice through it at 0. Whereas, of course, a similar function, negative 3x squared times x plus 2. This is still a cubic function. It still has that leading coefficient of negative 3, so it's still going to have the same end behavior, same roots. leading coefficient. You can also tell a lot by looking at the multiplicity of a factor. Let's do one more for safe measure. If f of x, I'll give you a hard one, is negative 3x cubed times the quantity x minus 4 to the 4th times the quantity x plus 7 to the 19th. Woo! Okay, if you were to multiply all just the x's out without distributing all the rest of the stuff, you would get negative 3x cubed times 1x to the 4th times 1x to the 19th. That would be negative 3x to the 3 plus 4 is 7. 7 plus 19 will give you 26. Oh, even power, negative leading coefficient, it's got to point down. So we have roots at 0, positive 4, negative 7. My function is pointing down, the left and the right. Okay, at negative 7, odd multiplicity, function slices through. 0, odd multiplicity, the function slices through. 4, even multiplicity, the function is just going to bounce off that positive 4. Okay, just one final wrinkle. Perhaps you have to find the roots. Perhaps they're not so obvious sometimes. So if we wanted to sketch f of x as x cubed minus 3x minus 10, oh, you guys are quite good at that. That would be the quantity x minus 5 times the quantity x plus 2. Oh, here's our friend the parabola with a root at negative 2, a root at 5. It'll look like this. Well, what if it looked instead like this? F of x equals negative x to the 11th plus 3x to the 10th plus 10x to the 9th. Don't be intimidated. We see that these terms each have at least an x to the 9th. I also don't feel like dealing with a negative leading coefficient, so let's take out negative x to the 9th. You're left with x squared minus 3x minus 10. Oh, which you know can be further factored, just like you did above. So this is a degree 11 polynomial with a negative leading coefficient. It's got to look like this at its ends. It has roots at 0, 5, and negative 2. On the end behavior. One more time. Oop, they all have bottom multiplicity, so we're going to slice, slice, and slice. Okay. 2 more examples for today. What if you have x cubed minus 3x squared minus 16x plus 48? Don't be intimidated. You guys know how to factor by grouping. Look at these two terms. What do they have in common? X squared, so take that out. Look at these two terms. What do they have in common? 16, so take that out. Again, I don't feel like dealing with this being negative, so let's take out negative 16. You get x minus 3. Now, these are two terms. What do they have in common? X minus 3. We'll take that full quantity out. You're left with x squared minus 16. Not fully factored because we have factors that are not all linear. They should all have an exponent of 1 when you're done. So, we know that's just x plus 4 times x minus 4. So this big nasty polynomial is simply a cubic polynomial with a positive leading coefficient of 1 with roots at negative 4, positive 4, and positive 3. Oh, it's not so bad. And behavior in. All unwritten multiplicities of 1. 1 is odd, so we're going to slice, slice, slice. One final treat for you today. Example 9. What if we were trying to sketch this polynomial, 2x to the 4th minus 13x cubed plus 23x squared minus 3x minus 9. Okay, I'm looking at this. I realize it's a 4th degree polynomial with leading coefficient positive 2. I know its end behavior is going to look like this. But unless I have another hint, I don't know how to factor this. There are 5 terms, so I can't factor by grouping. That was handy when I could split them into 2 pairs. I would have to have another hint. Now, the question would have to tell you something like f of x you put the coefficients down of your original polynomial, so 2, negative 13, 23, negative 3, oops, not the x, just the coefficients, and negative 9. Draw a line. This is cute. You remember this? Bring down the 2 and multiply. 2 times 3 is 6. Now add. Negative 13 plus 6 is negative 7. Multiply. Add. Multiply. Ooh, that's a mistake. Negative 7 times 3, come on. I'm sure you caught that on your own. Add, multiply. Much better. Add, multiply, and add. Ooh. So this is my new remainder. This is the coefficient of x. This is, new remainder, new constant, number without the x. New coefficient of x, new coefficient of x squared, and new coefficient of x cubed. You just go in reverse. This is the remainder, this is the number by itself, the constant. We'll go ahead and fill in plus signs for the ones that are positive. That means my function f of x is x minus 3, that factor, times the rest of it. 2x cubed minus 7x squared plus 2x plus 3. Now, I could try factor by grouping. They don't have anything in common other than x squared, take it out. They don't have anything in common other than nothing, take out a 1. Well, these don't have anything in common. So don't fear, this would be your hint. There would have to be another hint in the question. Like f of x has a factor of x minus 3 with multiplicity 2, meaning you can divide by x minus 3 2 times. So let's take this result, the 2x cubed minus 7x squared plus 2x plus 3. We'll put 3 in the basket because it's the root. We're going to divide again. Bring down the 2, multiply, add, multiply, add, multiply, add. Oh, this is nice. So we have x minus 3. We're just bringing it down. We're rewriting this whole business as x minus 3. That's coming from our factor. Times, I don't know. This is my remainder. Here's my constant. This is negative 1x. This is 2x squared. So that means 2x squared minus x minus 1. Oh geez, we're going to have to be able to factor this guy. I need two numbers that multiply to negative 2 and add up to negative 1. Oh, negative 2 and 1. Okay, so we have x minus 3 times x minus 3, or x minus 3 squared, times 2x squared. We're breaking up this middle term into negative 2x plus 1 minus 1. Just bring that guy down. Factor by grouping. These guys have 2x in common, so take it out. These guys have x in common. I'm sorry, nothing in common, so take nothing out or take a 1 out. These guys now have x minus 1 in common, so take that out. What you're left with is 2x plus 1. I know I'm fully factored because the x's have exponent 1. This factor has multiplicity 2, but the x has an unwritten exponent of 1. So now I'm done factoring, which means it'll be easy for me to find the roots. There's a root at 3, with multiplicity 2. I'm going to star that so I remember. There's a root at 1. There's a root, I don't know, wherever 2x plus 1 is 0. It's degree 4. Oh, here's its end behavior. It's got to go like this. It's got to go like this. Let's connect the dots. Okay, negative 1/2, multiplicity 1, so slice. 1